In this episode, we're going to slow down and get very practical about primitive data types, because a surprising number of automation failures are not caused by complex logic, but by simple values being treated as the wrong kind of value. When you are new, it is easy to assume that data is just data, and that if something looks like a number or looks like true or false, the computer will understand what you meant. In real automation, especially when your scripts touch cloud resources and security-sensitive settings, that assumption can quietly turn into misconfigurations that are hard to detect until they cause an incident. Primitive types are the basic building blocks like strings, integers, floating-point numbers, and booleans, and they shape how comparisons behave, how conditionals decide, and how data moves between systems. If you learn to treat types as part of the meaning of the value, you stop relying on luck, and your automation starts behaving like a dependable operator would behave: cautious, explicit, and predictable. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A primitive data type is not just a label because it changes the rules of the game for that value. A string is text, and text is compared and transformed differently than numbers, even when the characters inside the string look like digits. An integer is meant for whole numbers, and it behaves predictably for counting, indexing, and threshold checks, which are common in operational scripts. A floating point number is used for values that require decimals, like percentages or durations that are not whole seconds, but it brings rounding behavior that you must respect. A boolean represents true or false, and that sounds simple until you realize many systems represent boolean-like states as words or numbers that must be interpreted. When you understand these types as different categories of meaning, you avoid writing automation that accidentally treats a count like a label or treats a label like a number, which is where silent failures begin. Silent failures are the most dangerous kind in operations because they look like success from a distance while producing the wrong outcome underneath. A script might run without errors, return a status that looks normal, and still make the wrong decision because a comparison happened as text instead of as a numeric comparison. In cloud security contexts, that could mean applying a policy when it should have refused, or skipping a safety check because a value appeared false when it was actually a valid zero. Silent failures also show up when type coercion occurs, meaning the system automatically converts one type into another in a way that seems convenient but changes meaning. Automatic conversion can be helpful in small examples, but in automation pipelines it can hide mistakes and let bad assumptions travel far. When your automation is connected to access control, logging, or configuration management, hidden mistakes can create exposure or downtime without obvious alarms. Preventing silent failures starts with treating types as something you manage deliberately, not something you hope will work out. Strings deserve extra attention because nearly everything arrives as text at the edges of an automation workflow. Configuration files, environment variables, log lines, file names, and many pipeline outputs are all strings until you intentionally interpret them as something else. The biggest beginner trap is assuming that a string containing digits behaves like a number because visually it feels the same, but comparison rules for strings can be completely different. Text comparison tends to follow alphabetical ordering rules, so values that look numerically larger might be treated as smaller depending on their characters. Another trap is whitespace, where a value that looks correct on screen includes hidden spaces or newline characters that break equality checks. In cloud operations, string mistakes often appear as incorrect resource identifiers, wrong region names, malformed paths, or mismatched tags, which can cause automation to touch the wrong resources or fail to find the right ones. The safe habit is to normalize and validate strings before using them in decisions, because decisions are where risk concentrates. Integers and floating point values are where you learn the difference between counting and measuring, and that difference matters for reliable automation behavior. Integers are ideal for counts, indexes, retry limits, and fixed thresholds, because they avoid rounding surprises and make boundary checks straightforward. Floating point values are useful for measurements like CPU utilization percentages or time durations that include fractions, But floating point math can produce values like 0.30004 when you expected 0.3, depending on how numbers are represented internally. That tiny difference can matter if your script compares against a threshold and sits right at the boundary, creating unstable behavior where actions trigger on one run and not on another. In security and cloud contexts, threshold logic is everywhere, from rate limiting to alerting thresholds to deciding when to rotate keys or scale services. The safe approach is to pick the numeric type that matches what you are doing, convert inputs carefully, and compare values using a strategy that accounts for rounding where needed. When you treat numbers as precise tools rather than vague quantities, you reduce the chance that automation flaps between states or makes inconsistent choices. Booleans are powerful because they force clarity, but they are also a common source of misunderstandings because many data sources express Booleans indirectly. You might see states like enabled and disabled, on and off, yes and no, or even numeric codes like 1 and 0, and those must be interpreted intentionally. A beginner might treat any non-empty string as true, which can lead to a surprising bug where the string false is treated as true simply because it exists. That kind of bug is especially painful because the script looks correct at a glance, and the failure is quiet. In operational automation, Booleans often control whether a dangerous action is permitted, whether a security check is enforced, or whether a deployment step proceeds. So Boolean confusion can create real risk. A safer design is to parse Boolean-like values into actual Booleans early, validate that the input is one of the allowed representations, and refuse to proceed when it is ambiguous. When your automation can say, with confidence, this condition is true, you reduce the chance that the rest of your logic is built on sand. Null and missing values are another area where type discipline prevents subtle failures, because missing data is not the same thing as a value that happens to be empty. A missing value might mean the system did not provide the field, a lookup failed, or a prior step did not run, and each of those situations can require a different safe response. An empty string might be a valid value in some contexts, such as an optional description field, but it might be invalid in others, such as a required identifier. A numeric 0 might be a valid threshold or a valid count, but it might also be used as a placeholder when a conversion failed, which can hide an error. In cloud security automation, missing values can lead to incomplete policy documents, skipped validation steps, or default behaviors that are less secure than intended. A fail-safe approach treats missing required data as a reason to stop or to take a conservative path, not as a reason to guess. When you make a clear distinction between missing and empty, you improve both safety and troubleshooting because you can tell what kind of problem you are dealing with. Type coercion is where many silent failures begin, and understanding it gives you an operator's advantage. Coercion is the automatic conversion of one type to another, such as turning a number into a string during concatenation or turning a string into a number during arithmetic, depending on the language and context. This can feel helpful because it reduces the amount of explicit conversion you write, but it can also hide mistakes like comparing a numeric threshold against a string value that was never parsed. Coercion can also cause Booleans to behave unexpectedly when values are treated as truthy or falsy based on language rules rather than based on your meaning. In automation that integrates multiple systems, coercion problems often appear when one system exports values as strings and another expects numbers, or when a configuration source represents true and false as words. The safest habit is to perform conversions explicitly, early in the workflow, and to treat conversion failures as real failures rather than quietly substituting defaults. That is how you keep your automation honest. Equality and comparison operations are a common exam theme because they look simple while hiding type pitfalls. Equality is not just asking whether two things look the same, because it is asking whether they are the same kind of thing with the same meaning. If you compare a string and a number, you might get a result that is surprising, or you might get a result that varies across languages and environments, which is bad for predictable automation. Ordering comparisons, like greater than and less than, are even more sensitive because string ordering and numeric ordering are different worlds. In cloud automation, comparisons show up in decisions like whether a deployment version is newer, whether a latency value exceeds a limit, or whether a security posture score is below a threshold. If your types are wrong, these comparisons can cause actions at the wrong time or prevent actions when they are needed. A disciplined approach is to ensure that both sides of a comparison are the same intended type, and that the type matches the concept you are comparing. When comparisons reflect meaning, they become reliable decision points instead of random behavior. Parsing is the bridge between raw input and typed values, and it is one of the places where operator-style caution pays off. Parsing means taking a string and converting it into a number, a boolean, or another structured form, and the most important part is not the conversion itself, but the validation around it. A string might contain commas, extra spaces, unexpected units, or characters that make it invalid, and a naive parser might fail loudly or, worse, succeed in an unintended way. In cloud security workflows, parsing often involves interpreting policy values, reading configuration thresholds, or extracting signals from logs, and errors here can ripple through the whole automation run. A safe parsing approach includes trimming and normalization, checking that the format matches expectations, and rejecting values that are ambiguous. It also includes deciding what to do when parsing fails, and for risky actions, the safe answer is usually to stop or to take a conservative path. When parsing is treated as a security boundary, your automation becomes more resilient. Another common source of silent failure is the use of sentinel values, meaning placeholder values like -1, empty strings, or special words used to indicate an exceptional state. Sentinels can be convenient, but they can also be dangerous because they are easy to forget and easy to misinterpret later. If one part of your code treats -1 as no data and another part treats it as a real count, you can get decisions that look logical in isolation but are wrong in the full story. In security-oriented automation, sentinel mistakes can cause skip checks, incorrect scoring, or accidental allowances when a missing value should have triggered a block. A safer approach is to separate exceptional states from normal values explicitly, such as treating missing data as missing rather than as a fake number. This also makes your conditionals clearer because they can branch on a real exceptional condition rather than on a magic number. When you reduce reliance on sentinels, you reduce the number of hidden rules people must remember to maintain the script safely. That reduction in hidden rules is a direct reduction in operational risk. Type discipline also matters when data crosses boundaries between components, such as moving from a script into a pipeline stage or from one service into another. Even when everything is working, different systems have different expectations about types, and mismatches can cause subtle issues like values being treated as strings in one place and numbers in another. Structured formats like JavaScript Object Notation, JSON, often preserve type information, which is helpful, but only if your workflow maintains that structure and does not flatten everything back into text unexpectedly. A common beginner mistake is to stringify structured data too early, then perform text operations that accidentally change numeric values or Boolean flags. In cloud operations, boundary crossings happen constantly, such as passing values between orchestration steps, storing state for later runs, or integrating with monitoring systems. Safe automation treats boundaries as places where you recheck assumptions, including type assumptions, because boundaries are where silent conversions occur. When you make boundary behavior explicit and deliberate, you prevent failures that only appear in certain environments. A practical operator mindset is to design your automation so that type problems become loud early, not quiet later. Loud early failure means that if a required value is missing or of the wrong type, the script stops before it performs risky actions, and it produces a clear reason that can be used for troubleshooting. Quiet later failure is when the script continues with incorrect assumptions and only fails after it has already caused side effects. Or worse, it never fails and leaves the system in the wrong state. This is closely tied to fail-safe conditionals because you often use type checks and validation checks as gates. It is also tied to functions because a well-designed function can enforce type expectations at its interface, making the rest of the code safer. In cloud security contexts, loud early failure protects you from accidentally applying partial policies, mistagging resources, or bypassing validation due to malformed data. The exam tends to reward designs that detect invalid states early and handle them consistently. Consistency is what makes automation trustworthy when multiple people depend on it. As you pull these ideas together, the main point becomes clear. Primitive data types are not a beginner detail. They are a reliability foundation. Strings, numbers, booleans, And missing values each carry meaning, and that meaning shapes how your automation thinks, decides, and acts. When types are handled deliberately, comparisons become reliable, conditionals become safer, parsing becomes predictable, and integration across systems becomes less fragile. When types are handled casually, your automation can appear correct while making wrong decisions that are expensive to diagnose, especially in cloud environments where changes propagate quickly and permissions can amplify mistakes. The mindset you want is simple and professional. Convert explicitly, validate early, compare like with like, and treat ambiguity as a reason to stop or to be conservative. That mindset prevents silent failures, which is the goal the title is pointing you toward. If you build this type discipline now, you will find that many other automation concepts become easier because you can trust the values your code is using, and trusting your values is the first step toward trusting your automation.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.